Okay, so where should we start at? Okay, so let's start with the conventional. So what do I need to write out? We can start either one. We get ALCL. Okay, so ALCL, are you sure? ALCL 3. Okay, solid, liquid, gas, or aqueous? Are you sure? It says solution, so. Sodium nitrate. I'm sorry, thank you. Silver nitrate. I was thinking about another problem. Silver nitrate, Ag. Solid, liquid, gas, or aqueous? You got to remember it, right? So solutions are always going to be in water. Yep. Okay, and that's going to yield. So what are we making? AgCl. That's right. And how did you know it was a solid? Because it says precipitate. Yeah. Okay. And so parentheses NO3. I'm running out of room. Shift it. One day I'm going to get it worked out that I have this all, so I don't have to shift things. Oops. Solid, liquid, gas, or aqueous? Okay, is it balanced? No. What do I need to do to balance it? A 3 where? Right there and right here. Oops, I forgot a 3 here. Okay. So what would be the total ionic equation? Okay. Okay, so let's start off with the aluminum. Al, is it a solid? It's aqueous and it's 3+ because it's an ion, right? Yes, you do, because you have to recognize that it's an ion. Ions are going to behave differently than the solid. Plus 3, chlorine, Cl minus. Okay, aqueous. Plus 3Ag plus aqueous plus you said 9? Is it 9? 3. NO3 minus AQ. And that's going to yield 3AgCl. So why is it AgCl? Why doesn't it break up? Because it's a solid. Solid liquids and gases don't break up. Liquid and gases, yep, don't break up. That's right. That's right. Plus three plus plus oops. You mean 3 nitrate? Okay. So who are our spectators? What are spectators? They don't do anything. Exactly, they're watchers. So who are my watchers? The nitrate and the aluminum. Okay.
Oh, I'm not quite sure I understand what you mean by not do anything. Because to me, it looks like the aluminum.
Is it matching up with anybody? Is it hooking up with anybody?
Yeah,
Because if you look on both sides of
it's
the equation, isn't it exactly the same thing?
not.
Al3 plus, Al3 plus.
I'm confused.
What do you mean?
Uh, so what I mean is that I see aluminum with the chloride, and then on the other side, aluminum with the nitrate.
No, you don't see the aluminum with the chloride because it dissociates. If you take a look, the aluminum is all by itself, right? The chloride is all by itself. The chloride ion, the aluminum ion is all by itself. Do you see what's circled?
Yes.
Okay. So when we dissociate, what's really happening is that the water is disrupting it, right? And if it doesn't match up with anybody, it's not doing anything in the reaction. It's just bringing the other guy to the party. So aluminum just brings chloride to the party, right? And then it just sits there. It does nothing else. So it's not really doing anything other than providing a way to get to the party.
Okay.
And so what you want are the people that are doing stuff, or the elements that are doing stuff. So in this case, the chloride and the silver, they get together to form silver chloride, a precipitant, right? The other ones are still in solution. They're going to remain in solution. They're not going to do anything. They're just going to sit in solution.
Okay.
Right. And so that's the reason why these guys don't come together. They really don't come together. They're still aqueous. They're all in solution. Does that make sense?
It's gonna take me some time to digest that, but
Okay.
sure.
Okay. So then who are the active participants at the party? Who are the ones that hook up and go home with somebody else? Okay, so we have the 3 chloride ions. And the 3 silver ions. And they're going to come together to make the 3 silver chloride. Okay. Questions? Concerns? Pretty straightforward.
So in this form of the equation, it's easier to identify the spectators. Is that why this
No,
form is important? Or
yeah, the total net equation is just, it lets us know the ones that are really involved in the equation, who are really active in the reaction, right? Because the other ones that we really don't care about them, they were just to get the other vehicles there. So the aluminum and the nitrate were just to get the other chemicals there so that we can get that to happen.
okay. I guess it's just when you say it like that, it's like, well, why didn't we just use silver instead of silver nitrate?
Well, because we can't use silver metal because it's not in the ionic form. It's a lot easier to use the ionic form to get to where we want to be rather than using the full metal. And the metal is going to behave different than the ion does, right? Because this here is a double replacement. If I just stuck metal there, right, and I just stuck chlorine there, right, it's going to behave differently, and it's going to take a little bit longer, and it could cause a more volatile reaction, or it could involve or result in a different reaction than we anticipate. And so here we're setting it up because we're using the silver ion rather than the silver metal. They're not always going to behave exactly the same way. Do you understand? Because the ion has different characteristics than the metal does.
Yeah, I think at this level, I understand. Thank you.
Okay. Okay, questions? No questions? Good. Okay. So now we have a single replacement oxidation reaction. Okay, in this single replacement oxidation reaction, we have an iron nail dropped into a solution of hydrochloric acid. I want you guys to predict the products, and then I want you to give me the total ionic equation, the net, the conventional equation, the total ionic equation, and the net ionic equation. Okay, an iron nail. What is the chemical formula for an iron nail? Fe, okay. Fe solid, okay. Can you guys see the slides on the other side? Robin? Okay. What is the chemical formula for hydrochloric acid?
HCl,
Okay.
aqueous.
And what are we going to get on the other side?
You're gonna get
We're going to get what?
hydrogen and iron chloride.
H2? Is that a solid, liquid, or gas?
That's gonna be a gas.
And is it iron chloride? Is that the name that we're talking about? Are you sure?
Um,
I don't know. You guys tell me. Well, it would be called ferrous if it's. Okay, so this is an interesting one. So is it iron? Because is it iron a transitional metal?
yes.
It's going to require the Roman. Well, we know it requires a Roman numeral, but what Roman numeral would it be?
Iron
It's
1?
actually 2. It's a typo in the handout. All right, just testing it. Yeah. So it has it as if it's iron 3. It's actually iron 2. All of the metals except for aluminum, silver, and cadmium will be 2 except for aluminum, cadmium, and silver. Silver and cadmium are +1. Aluminum we know is 3. Okay. All transitional metals, I should say. Yeah. All transitional metals are going to be a +2 when you do a single replacement reaction. Okay. Yeah. Yeah. So there are special circumstances that we can get iron 3, but that requires some more heat for us to get to that point. So it should have been a +2. Yes. No, it just works with a single replacement reaction. Almost like 99% of the time, it's going to be a +2 if it's a transitional metal. Okay. Except for silver. Silver is always +1. Cadmium is always +1. And aluminum, you know, as a post-transitional metal, that's always going to be a +3. Yes. The Roman numeral does indicate that's true, right? But it's when we're writing the name out, right? Not when we're writing the chemical formula. Okay. Okay. Solid, liquid, gas, or aqueous. Aqueous. Okay. Is it balanced? No. What do I need to do to balance it? And you guys are getting really good at this. Starting to make me worry a little bit. I have a fever? Am I in heaven?
No.
I'm still in Kalinga. Okay. Okay, so this would be the what equation? Conventional. Okay. So the total ionic. Did we lose like 10 people?
There's nobody here.
Everybody's like, they're pre-spring breaking.
I thought about it.
Yeah, no, it isn't. Because the exam is going to cover a lot of this stuff, right? And so they're going to be crying. Okay, so what am I going to do for the total ionic equation? Separate them all out. So iron solid. How am I going to write that? FES? Are you sure? It's a solid, right? It's not going to have a charge. Its charge is always neutral, right? So remember, it's the element. When they're talking about the element itself, it's always going to be neutral. It has the same number of protons as it has electrons. Okay. You guys want to remember that. That is the most common mistake made. Okay. What else? H plus. Okay. And we need to put what next to it? AQ. Aqueous, right? Remember, it's aqueous. It stays aqueous. And chlorine ion or chlorine? Chlorine ion, which has a negative charge. And there should be how many of them? Okay. And that's going to yield H2. Aqueous gas. That's right. because hydrogen, when it's a diatomic, is always a gas. Yep. Unless it's an ion, then that's right.
Now it's gonna be
Fe2, that's right.
Now we're-
Fe2 plus aqueous. And 2Cl, 2Cl minus. So why is it 2Cl minus instead of Cl minus 2 subscript? Say that again.
I would say it's because you're breaking everything out.
It's because we're breaking everything out, right? And we know that what's holding it together is the Fe2 plus, right? That's what's causing it to stick. So if you don't have the Fe2 plus, it's not going to stick, right? So they're individuals. Okay. Okay. So spectators, 2Cl. Okay. So then the total, I'm sorry, the net ionic equation. That's right.
Oh, okay. So in this case, it's the chlorine that brought the hydrogen for the ride. Is that
That's right. Yep.
okay?
So is that making a little more sense now?
A little bit. This is going to be slow for me.
You didn't go to enough parties. That's what the problem is. Yeah, when you go to enough parties, well, we know that you already have this worked out. Yeah, creeping in at 2 o'clock in the morning, right? He doesn't even remember what he did.
No, well, I remember some part, okay, like the beginning, middle, end of the night, I was like, "Eh, somehow, well, not my bad, it was someone else, but it was someone's bad." I don't know how to change them there, but we're in someone's, I ended up like, I was asleep, it was like noon, and I was like, oh, no.
Keep digging, Wilson. Keep digging. Okay.
Yeah.
Okay, so kind of clear, pretty straightforward. Or it's starting to click a little bit. Okay, so let's see if we can get a little bit further. Okay, so the reaction between zinc and silver copper, copper to nitrate. I just want silver today. Just think about all that silver. Okay, so reaction occurs between a piece of zinc, a reaction occurs when a piece of zinc is dipped into a solution of copper to nitrate. Write the conventional, the total ionic, and the net ionic equations. Okay, so where are we going to start at?
I'm going to start with zinc, solid.
Zinc solid. Okay. And
plus copper parentheses NO3 2 aqueous. Yields zinc parentheses NO3 2 aqueous plus copper solid.
Do you guys agree with him?
I didn't know what you just said. Sure. Yeah. Go you.
Yeah, it's weird because you can't hear everything anymore. So he said zinc solid plus copper 2 nitrate aqueous yields zinc 2 nitrate or zinc aqueous. Oh yeah, thank you. And copper solid. That's right. Cu solid. Okay, is it balanced? Yes, it is. We have one copper, one zinc, 2 nitrates, 2 nitrates. Yeah. Okay.
So then for the total
so how do I
ionic,
separate them?
it'd be zinc solid and no charge because it's the element.
You can say it as well too, so we can hear it on this side as well. Zinc solid.
And let's see, copper 2 plus.
Copper 2 plus. Do you guys agree with that?
And then plus the nitrate.
Am I forgetting anything on the copper 2 plus?
Oh yeah, the aqueous.
Aqueous. Okay. And then you said
The nitrate 2 aqueous. And then
is it nitrate 2 aqueous? Or is it 2?
Oh, okay.
2
2
nitrate.
nitrate. And then you have to add the charge.
That's right. And that's going to yield
the zinc 2 plus aqueous.
and
The 2 nitrate minus. Let's see, and then you're gonna get a
aqueous.
right, the aqueous, and then you're gonna get the copper.
Copper solid.
Yeah. Now, what I'm kind of confused about is because it was copper 2. Is that copper 2?
Nope.
Or
It's not
okay,
copper 2. It's going to be copper solid.
copper.
So
Okay.
that brings us to the next topic after we finish this. What was that? He asked, he says, since we started out with copper 2, shouldn't that be also copper 2? It's
Okay.
solid. What was that?
But it's just the element.
Solid. And we will talk about that here in a second. You're bringing me to the next point. So excited. So
Okay.
excited. I am. It is so cool. It is. It really is. Okay. But we'll finish with this stuff.
And
Okay.
good news is this
So-
is finally clicking. So
Who is the spectators?
the
Nitrate is the
nitrate.
spectator.
Yeah.
Nitrate is the weirdo. Yeah, it is. I'm gonna have to use that one actually. Now I will. So. Okay. Piece of cake? Not too bad.
Go past the 3D circus.
You said the 3-ring circus?
You saw the circus tent?
No, I didn't see the circus tent.
Well, they had circus yeah, circus in town for a weekend. I mean, I drove past it and it looked like you would get mugged there. Like someone will do a flip and then just like stab you and then like flip out.
Okay.
Dude, it was so creepy. I was like scared. I was so scared to go over there. No.
Okay, so this is an example of what we call a redox reaction. Redox standing for reduction and oxidation. You guys remember that? Okay, so reduction means gain of electrons. And oxidation would be loss of electrons.
Oh, so the copper gained 2 and the zinc lost 2?
That's right. And it's always about give and take. Somebody's going to be gaining, then somebody's going to be taking, right? So somebody's going to be losing.
So then that's why it's just copper solid at the end, because
That's right.
it gained 2 electrons. Got it.
That's right. So copper is going to be gaining the 2 electrons. So gaining 2 electrons means it's being reduced, right? And then the zinc is going to be losing electrons. So that's going to be oxidized. Okay. Okay, you guys see that? Got it down? And I love putting this on the exam, just for the record.
Exam.
So, you guys have heard of the lithium ion battery? It's incredible, isn't it, right? What was that? Yeah. So, it's based upon this ion, you know, the one is gaining the electron, one is losing the electron. It's using that energy that's being transferred there, right? That's the beauty of it, right? So look at what chemistry does, right? It's incredible, right? Isn't it? It's fucking incredible. I mean, I was sitting there. Okay. So the car I was driving, right? I went and test drive a car this week, right? Right, not the Tesla. It was another Kia. It was the same Kia. I test drive it a second time. I'm like, oh my God, I was in heaven. It was like a cloud and everything. And I'm just thinking, this is pure chemistry. It is. It's pure chemistry, right? It is. Yeah. And I was sitting there talking to him, and he's like, no, it's pure electric. It's a pure electric vehicle. It's pure chemistry, right? Because it's using a lithium ion battery, right? Yeah.
So
the EV6. Yeah, oh, it is. It is heaven. It drives itself. I was just like, oh my God. It was just such heaven. Yes, it does. It has the new logo on it. Yeah.
So what's the chemistry that's I think there's like a push for an iron battery or with an iron electrolyte. Is that just
There is
basically
a push. Yes, there is a push because iron is more common, right?
Okay.
And lithium lithium is a lot more volatile, but you get a lot more energy out of lithium because it is more volatile.
Oh, I see. So there's a trade-off.
But I
Since-
didn't buy it yet. That's the one that I want. I was just like, it drives incredible. And so I was just like, I was talking to the salesman. about chemistry and everything like that. And he's looking at me and his eyes glaze over and everything. And I'm like, okay. What was that? I think I want the blue one. There is a nice, really nice blue one. Yeah. So, yeah. Yeah. Yeah, you know, I have to replace my little blue car with something blue, right? So, okay. Okay, now back to chemistry. So now that we went totally.
I'll buy the car. I said it was awesome.
Yeah. Okay, so that brings us to our next topic. This is so cool, right? So cool, right? So this is called the activity series. The activity series is kind of like a hierarchy. You know, have you talked like the class system and stuff like that? Poor people, rich people, right? Okay, it's kind of like a class system, right? So these guys are on top, right here. These are on top of the activity series. So they can actually replace anything that's below them, okay, in a chemical reaction, particularly when we're talking about aqueous types of solutions, okay? So let me give you an example, because we just talked about, what was it? It was zinc and copper, right? So in that example, we had zinc and copper. So we had zinc metal replacing the copper 2 nitrate. And we know that we got a reaction because they showed us that reaction. It turned black and all that good stuff. So we end up with zinc nitrate plus copper. Oops. Change that color so you guys can actually see it. Okay.
So in terms of,
Okay, go ahead.
oh, in terms of this hydrogen, is this like I don't want to say rust, but is it kind of like that type of environment, or is it a corrosive environment?
Let's talk about that because it's not quite, because rust is a little bit of a different beast.
Okay.
Okay, so because that deals with oxidation, but that deals with oxidation by oxygen, right? So partially, and water, I guess. We'll talk about it. I'll explain it to you in a second. Okay, so for instance, we look at zinc. Where is zinc located on the hierarchy? Right there. Okay. Now, where is copper? Is it below it?
That's
Okay.
last class.
So zinc can replace copper, but copper can't replace zinc. Okay. So what I'm saying is that if we had copper here, copper solid plus zinc nitrate, no, it won't. It won't. It won't be the same thing. Nothing will happen. Okay. It's going to be NR for no reaction. Okay. So it works one way. If you're on top, you can replace the people below you, but the people below you can't replace the people on top. Kind of like our hierarchy system, right? Poor people can't replace rich people, right? No. No, it doesn't work that way. Not really. Yeah, that's a whole nother conversation, but not really. Yeah. So yeah, social class issues. A lot of our what we believe is to be overthrows were actually led by other rich people. So and instigated by other rich people. Yeah. Okay, so do you guys understand that? You see how that works? Okay, so let's test this out. Okay, so I'm going to write the chemical equation. I want you to tell me what the product is going to be, or tell me it's going to be no reaction. Okay, You guys are ready. So, but you were talking, but before we get started, we'll talk about the hydrogen. So here, hydrogen makes reference to hydrogen that's going to either be in water, it's going to be in steam, or it's going to be in an acid. These guys can replace hydrogen in water, in steam, and in an acid. These guys can only replace hydrogen that's in steam or an acid. These guys can only replace hydrogen that's in an acid. And these guys can't because they're below hydrogen, right? They can't replace anything. Okay. So let's do a test run here. You guys ready? We've got to work on that one there. Okay, so we have, let's put Mg NO3 plus
And
SR.
this is a non-exhaustive list, is that right?
This is so you're basically asking me, is the list bigger than this?
Yeah,
It will include all, there's a list that actually includes all of the metals, but this is just to give you an example of how it works.
okay.
What was that? SR, yeah. And that's a solid. And that's AQ.
Yeah, it is.
Okay.
Over here, right? Like, all right.
Yes. It's hierarchy still. Yeah.
So I think the first two would have reactions and then the last one would be no reaction.
Okay, so we have predictions here. Are you guys ready? Okay. A firm handshake. You guys have firm handshake bets. Okay, so you guys ready? So the first one, is there going to be a reaction? There is. Strontium is right here. And magnesium is down here, right? That's right. The rich person can replace the poor, right? There you go. So then we would get SR NO3 2 plus Mg solid. Okay. It doesn't matter. It just matters who's on top. Okay. So there are some that actually will fall in the same, like at the same level, but usually they're written at the same level. These, they're different. Okay. So we have the next one. No reaction. That is correct. It's still a hierarchy. Yeah. There are some, like I said, they're really close together, but then usually they're listed at the same level.
So same level or below, there's no reaction. Is that
That's
for the
right.
most?
Yep.
Okay.
If you're at the same level, there won't be a reaction. Yeah, if there's a difference, yeah. It'll take it longer to react. So like, for instance, in the case of, if we had the other way around where we had chromium and magnesium, right? It would react, but it would take longer for it to react. It's going to be a slower reaction. No, bleach and ammonia reacts very fast. So that's different. Yeah. Okay, what about the last one? That's right. No reaction, right? Clearly no reaction. Okay, you guys got it? You guys, not too hard? So let's see if we can make it a little bit harder here. Okay, you ready? Yeah, this is definitely going to be on the test. Right? I get so excited about this. It just makes me perk up and everything. So. Okay, so everybody got this down, or do you need a second? Good? Okay, good. Okay. Okay, so let's say we have oops, and I should do this. Okay.
Okay, so that'll be reaction, reaction, no reaction, and no reaction.
He said reaction, reaction, no reaction, no reaction. You agree? Yeah. I'll let everybody get their answer, and then I'll tell you what the answers are. I should add one more. Let me move this up to the top so you guys can see it. Can you guys see it better now? There. There's 5, yeah. Always tired. Never enough sleep. I average about, well, lately it's been about 4 hours of sleep a night. So. Only on the weekends. Okay. Are you guys ready? Okay. So let's start with the one here, then we'll save that one for last. Okay. So the potassium water liquid with potassium. It will replace it. So I should get potassium. It should be aqueous. It's going to stay. Okay, so typically, if something is aqueous and another metal is replacing that system in aqueous, it's going to be aqueous. Okay, unless it forms a precipitate, which is rare. Okay, usually if it's nitrate, nitrate never forms a precipitate. Okay, and I'll show you that here in a second. We're building up to it, working our way to it. If it's a single replacement reaction, then a single replacement reaction with an aqueous solution, right? Then, yeah, aqueous solution, aqueous, right? Usually aqueous, right? Except for this is the case, it's liquid because it's water, right? Okay, so then it's going to be an aqueous solution, okay? So we get potassium oxide, AQ. Okay. Now what about steam? H2O gas plus magnesium solid. Okay. All right. So then we get, sorry, manganese. Manganese oxide. It's manganese 2 oxide. So plus That should be AQ H2. Yep. Okay. What about lead and water? No reaction. And what about, okay. And up here, it's liquid water. No, no reaction. That is correct. Yep. So you guys see how to use the activity series? Hierarchy. It's all about power. Right? No. Okay. So let's clear. Can I clear this? Everybody got this down? Okay. Again, this will be on the test, right? Yes. And it's a puzzle. It's a nice little puzzle. So think about all of the things that are being given to you. Okay. Okay. So oxidation and reduction can also apply to organic material. We've already gone over an oxidation reaction, right? And reduction reaction. It's just a combustion reaction. We know that in a combustion reaction, if we have organic material, we're always going to end up with carbon dioxide, water, either liquid or gas. Okay, but you need that oxygen to cause that oxidation, right? Keep that fire burning, right? So without oxygen, the fire does not exist, okay? So if we're burning anything, you're always gonna know that you're using oxygen from the air. So if they say something's burning, where's that oxygen coming from? Okay. And then you're always going to end up with carbon dioxide and water. Okay. You want to test this out? So here's the question. Right? The equation for the complete burning of ethane, C2H6. Carbon dioxide and water. If it's clean and perfect, it always yields carbon dioxide and water. What do you breathe? Yep. Like when the building catches on fire, where do you think the oxygen is coming from? The air. Yep. You get oxygen. You get oxygen. Still we're off oxygen, right? Yeah. Yes. That's right.
I wish I would always looked up over things. You get a car, and like.
Oh yeah, right now especially. I wish that I was at Oprah show, right? Come on, car, please today, car, please,
Where you give a key.
Okay, you guys ready? So, what would be the equation? C2H6, and it's a gas, plus O2. And that's going to make CO2 and water. Solid, liquid, or gas? Actually, it's
Gas.
gas for water. Because it's burning, right? Burning. Yeah. And O2, is that a solid, liquid, or gas?
That'll be a vapor, or I guess for gas.
It'll be a gas. That's right. Okay. Is it balanced?
Probably not.
Okay, so let's do some balancing. Okay. How many carbons do we have on the reactant side?
2,
2. How many do we have on the product side?
1,
How many hydrogens do we have on the reactant side?
6,
How many hydrogens do we have on the product side?
2,
How many oxygens do we have on the reactant side?
2,
And on the product side?
3.
Okay, is that balanced?
No.
Okay, so what do I need to do?
Let's put probably
Put a
the
what in front of the CO2? A 2?
3.
Okay. So we got to put a 2 in front of the CO2, so then that gives me 2 carbons. How many oxygens do I have now?
5.
I have 5. 5 oxygens. Okay. What about the hydrogen?
We need 3 on the product side as a coefficient.
Okay, so 3 there. So then that would give me 6. And how many oxygens?
7.
7. So 2 times 2 is 4 plus 3. That's a total of 7. So what times 2 will equal 7? Or 7 halves? 7 halves. But we know that we can't have a half of a molecule. So what must we do?
Find the lowest common denominator, or
So we multiply it all by what the denominator is. Multiply the whole thing by
2.
2. So if we do that, we end up with, and I'll write it at the bottom here. So we'll end up with 2C, 2H6 gas plus 2 times 7 halves. Should be 7, right? And that's a gas. And that's going to yield 2 times 2, 4 carbon dioxide. Gas. Plus, you said 6 H2O gas. Okay, so let's check to be sure. So we have 4 carbons over here. We have 4 carbons over here. We have 12 hydrogens over here. And 12 hydrogens over here. We have 14 and 4 times 2 is 8 plus 6, 14. Well, it worked out pretty well. Okay, not too bad. Okay. So you'll definitely see something like this on the exam. You see a trend? It's down here. Yeah. So 4 times 2 is 8 plus 6 times 1. Yeah. You were looking up top still? Yeah. Yeah. All right. Once my head's in the way, right? You're like, Dr. Henry, your head is too big.
I understand that I heard one ID. Not nice.
So,
Yes.
so this would be the empirical formula?
No, this is just the balanced chemical equation. Empirical formula would it only make reference to a single compound, and it would be the one that has the lowest common denominator. Like for instance, if we were looking at the ethane, it's CH, sorry, 3. That would be the empirical formula for ethane.
Oh, okay.
Yeah, don't forget that, because that's definitely going to be on the test as well too.
Okay. So it was like,
Empirical formula. Yeah.
okay.
Well, what I would say, focus on chapter 6, 7, 8, and 9. Yeah. Focus on chapter 6, 7, 8, and 9. All of the other builds up to 6, 7, 8, 9. So. And then anything that I specifically said, this will be on the test. Okay. You guys ready to move forward? And then we'll take a break. One more. Okay, actually, we're gonna take a break here. This will be our breaking point. I'm gonna introduce another concept. Okay, so let's take a 5-minute break, 6-minute-ish. Okay, so we've talked about single replacement reactions. You guys recognize that those are redox reactions. You're going to be able to identify who's being oxidized, who's being reduced, right? That's right. So now we're going to talk about a double replacement reaction. And in a double replacement reaction, we normally will get something that is going to form a precipitant, at least one precipitant. It could occasionally be 2 precipitants, but for the most part, it's going to be a single precipitant. Now, how do you predict that something is going to be a precipitant? Well, there's these rules. And we're going to show you, I'm going to show you the easy way, then I'm going to show you the hard way. Okay? Okay, you guys ready for the easy way? Okay. No, we'll do the easy, and then you'll appreciate after you do it the hard way, right? So, okay. So, if you guys have your handout. So if you turned out, or your periodic table handout, you got that? Okay, so there is a table that has pink and green boxes. I think you're already on. There we go. Yeah, that one. Perfect. Okay. So that's this table right here. Okay. So this is called the solubility table. So if you actually take a look here, so let's say, for instance, we had a compound that was making aluminum and acetate, right? Now, aluminum and acetate, when it comes together, it forms a precipitant. Okay. The way that we know that is because this guy is pink or orange or whatever color it looks like on the slide, right? It also says that it's lightly soluble, which means that it only dissolves a little bit. Soluble means it's totally soluble. It goes in solution. So anything that's soluble is in green, okay? So if it's pink, you're going to get a precipitant. Okay, so let me give you an example. So if I had aluminum nitrate, did you find it? You haven't found your periodic table? It's in that packet, yeah. Yours doesn't have color? Oh, it faded out. Let me give you another copy then, because I may have another copy. Yeah. Okay, and that's going to react with, let's say, sodium acetate. No yawning. What is up with you guys today? It's a Monday. It's the other Monday that starts with the T. Okay, so I have aluminum nitrate and I have sodium acetate. Okay, so my product is going to be, we know that this is a double replacement. Who's switching out with who? Aluminum is replacing sodium. So we get aluminum. Okay, and we know that acetate has what charge associated with it? It has a negative charge associated with it. So how many of them do I need to balance out aluminum? What is the charge on aluminum? +3. So then I only need how many? 3. Okay. So is that going to be solid, liquid, or gas? You'd use the table. So we look, aluminum acetate. It says slightly soluble, so that basically means it's going to be a solid, right? So. And we have sodium nitrate. Okay, so we look up sodium and nitrate. We'll have to look on the other slide. Hold on. I think. Here's sodium and nitrate. Okay, so then it would be aqueous. That's right. So if it's soluble, it means it's going to be aqueous. Okay, you see how to use the table? Yeah. Yep. And then now it's like all coming together. Okay, so you want to test, you want to do one more? Test it out? Okay, so let's see. Let's do, everybody got this down? Do you need a little time to get it down? Everybody got it, or are you good? Okay.
Same thing, you're taking a dog out back. It's your new saying is taking them to the gutter. Yeah,
So I corrupted you guys. Okay, are you guys ready? Okay. Okay, so what are going to be my products? Lead chloride. Lead, is it going to be lead chloride? What number? So it's lead 2.
2, yeah.
Okay, so lead 2 chloride. So we know that is going to be PbE, Cl2. Solid, liquid, gas, or aqueous. And solid, liquid, gas, or aqueous. Aqueous. Is it balanced? Yeah, last time we didn't balance it out. We need to balance it out, yes. So we'd have to balance it out. How do we balance it out? You mean the lithium chloride and lithium nitrate, yeah, okay. Piece of cake? Now, really, the table's so simple, right? See how it works? Okay, so now let me tell you what you'd have to do normally. When you're in 1A, this is what they have to do. Can I erase this? Okay, I give them this table, right? Or something equivalent to it. Actually, it's worse than this one, but okay, so these are the soluble compounds, right? So these are all the things that are soluble, right? So group 1 metals are almost always soluble. So group 1 metals. So you put group 1 metals with anything, it's almost always going to be soluble. Okay. Ammonium. Ammonium is going to almost always be soluble. Okay. Nitrate is going to always be soluble. So anything with nitrate is always going to be soluble. Anything with nitrite is going to be soluble, except for when it's with silver. Anything with chlorate is always going to be soluble. Anything with perchlorate is always going to be soluble. Anything with acetate is going to be soluble, except for aluminum and silver, because they precipitate. And the way that they figured that out is by doing the reaction. I wish there was a rhyme or reason to it. I have no idea. Okay. Silver, the silver ion and the aluminum ion. Yeah. Okay. Now, and you guys should actually have a copy of this as well. Do you guys have a copy of this? Should be in your packet. Yeah. I think you should. Not. Nope, I didn't. I didn't give you guys that. Okay. So I'll print out a copy for you guys. Yeah. Yeah. I need to hook you up with a really good copy, right? You're like, okay. So we have chloride, bromide, and chloride, bromide, and iodide ions are almost always going to be soluble, except when they're with silver, when they're with mercury 2 ion, and when they're with the lead 2 ion. And iodide. Yep. Soluble, except when they're with silver ion, the mercury 2 ion, and the lead 2 ion. Sorry, mercury 1 ion, not mercury 2. Mercury 1 ion. And lead, the lead 2 ion. Yeah. Okay. Compounds containing fluoride are always going to be soluble, except for when they're with group 2 metals, iron 2, iron 3, lead 2, and aluminum ions. Sulfate is going to almost always be soluble, except for when they're with group 2 metals. Carbonate, phosphate, oxalate, and chromate are almost always going to be insoluble. So they're going to always form precipitates, except when they're with group 1 metals and ammonia. Sulfide is always going to be insoluble, except for when it's ammonium and group 1 metals. And then hydroxides and oxides are always going to be insoluble, except for when it's with barium hydroxide, group 1 metals, or ammonium. Okay, so group 1 metals and ammonium will never react or will never form a precipitate except for lithium with phosphate. Okay, And that shows you, it shows you that on that table. If you guys take a look at lithium and look at phosphate. We're getting there. 9 more slides. Okay, so a solution of lead 2 nitrate and sodium bromide are combined. Write the net ionic equation for any precipitation reaction that may occur. Okay, where we're going to start at? You said PB NO3, just 1, 2, that's right. Solid, liquid, gas, or aqueous. That's right, because we know nitrate is always soluble. And Na, Br, and that's going to solid, liquid, gas, or aqueous, because that's a group 1 metal, right? And that's going to yield okay, sodium nitrate. And that's AQ, that's right. And lead 2 bromide, right? So that means I have 2 Br, and that's solid. Okay. Okay, is it balanced? What do I need to do to balance it? 2. Okay. Okay, so then our total ionic equation. Pb2 plus aqueous plus 2NO3, 3 minus aqueous plus 2Na plus aqueous, that's right. Plus 2 bromide. Yeah. And that's going to yield 2Na plus 2NO3 plus PBr 2. That's a solid, right? Okay. Spectators. Okay. So the total, I mean the net ionic equation. Okay. TBr yields okay. Questions? Concerns?
So,
Yeah. Yes,
question about the sodium.
yes.
I would have expected the bromide or the bromine to be the spectator,
Why?
but
Because isn't the bromide pairing up with the lead on the other side
um,
to form that solid?
yeah, that's true.
So then it's not a spectator, right? It's hooking up. It has a hot date with lead. Right.
Okay. So it doesn't matter. So the position doesn't matter in the reactants.
No,
And what I
because
mean by position, I mean sodium bromide. So the so basically an anion or a cation can be a spectator.
yes, yeah. So either could be a spectator.
Okay.
Yeah.
All right then.
Don't overthink it, Robin.
Uh, I'll try my best.
Okay. Okay, so you guys ready for the next part? Okay. No? Okay. Okay, so often we'll have what we call neutralization reactions. Neutralization reactions is basically when we use an acid and a base, and the product is going to be a salt and water. Okay, we've talked about this already. So typically, if we have a strong acid and a strong base that comes together, we're going to get salt and water. If one of the products is water or a weak acid, we can end up with salt and water, but it'll be slightly acidic because of that acid or that base, depending on what we have. Okay, so let me give you an example. Okay, write the conventional, the ionic, and the net ionic equations for a reaction between solutions of sodium hydroxide, hydrochloric acid and sodium hydroxide. Sorry, I was reading the last part. Okay, so let's talk about what we got. Okay, what are my reactants? Solid, liquid, gas, or aqueous? And solid, liquid, gas, or aqueous. And that's going to make H2O liquid. Yes. I like the way you laughed there. And NaCl. Liquid or aqueous? Okay. I'm just hard of hearing, I was just tested. She's
Oh, how did we just determine that the sodium chloride would be aqueous?
because if we put it together, sodium is a group 1 metal, right?
Oh, and they're all soluble.
That's right.
Okay.
Okay.
Got
So our total ionic equation. So do you want me to repeat the question? The question was, how do we determine that sodium chloride was aqueous? And then I said, we know that the rule is all group 1 metals are going to be soluble, right? Regardless of who they're with. So we know that when they come together, it's going to be aqueous. Okay. Okay, so the total ionic equation. So H plus, is that right? AQ plus chloride, Cl minus. Oh, first off, is it balanced? Okay, good. Because otherwise we're just spinning our wheels there. And then Na plus AQ OH, or OH minus AQ. And that's going to yield, you said, it's going to be H2O. And why don't we break it up? Because it's a liquid. That's right. We don't break up gases. And yeah. Okay. And then chlorine or chloride. Negative. I forgot my plus there. Okay. Spectators. Chloride. Sodium. Okay. So our net ionic equation. Hydrogen plus hydroxide aqueous yields water. Did it work out for you? Thank you. Excellent. That was good. Oh, you made a couple. Good. Okay. Questions? Concerns? Cash? Yes.
So in terms of the net ionic, that tells us like what's actually going on.
That's right.
But but it doesn't mean necessarily like that sodium chlorine or chloride is useless or anything like that. That's just not part of the reaction.
So it's useless for that reaction because they're not going to do anything, right?
Right.
So, but it doesn't mean
like,
that sodium chloride is useless. It just means for this reaction, they're useless. Does
okay.
that make sense?
So, but we could have used this reaction if we wanted to get the sodium chloride, right? For another use.
Yes, you can use this reaction to get the sodium chloride for another use. Yes,
But
because what you could do is boil off the water, and then you'll just have the salt. Yes.
okay.
Yeah.
So, but so net ionic means in more terms of what's actually happening at the chemical or the molecular level.
That's correct.
Okay.
Yes. Yes. Okay. Questions? Concerns? Okay. Let's go ahead and clear this. My arrow went haywire. Okay. So now that we've done this hard work, let me talk to you about some special cases, or what we like to refer to as exceptions. You don't like those? Okay. So when we get hydrogen ion and the carbonate ion coming together, we get carbonic acid. Carbonic acid is not stable. It actually breaks down to carbon dioxide and water. Okay. So the same thing happens with sulfurous acid. So if we get the hydrogen ion and the sulfite ion coming together, we get sulfurous acid, which breaks down to sulfur dioxide and water. The same thing happens with ammonium hydroxide. So if we get ammonium and hydroxide coming together, they form ammonium hydroxide. It breaks down to ammonia and water. Okay. Yes, you will have a question sort of like this. Yes. What was that? Okay, so here's an example. A reaction between solutions of sodium carbonate and hydrochloric acid. Write the conventional total ionic and the net ionic for these equations. Okay, so what do we have? Sodium carbonate. What is that? Na2, CO3, solid, liquid, gas, or aqueous. Okay. And hydrochloric acid. And we know that that's going to yield aqueous.
Oh, CO2 and water.
That's right. CO2 and water.
Or would it be preferred to do the intermediate? Like,
You can do the intermediate, long as you remember to use the arrow to go to the products.
okay,
Or what I always do is I kind of put this together and I put H2CO3 on top so that I remember, okay, it broke down to those.
so that's it's like a
Well,
single
is it
displacement
balanced?
with a decomposition.
Okay, so let's go ahead and balance it. What was that, Robin?
So it's a single displacement with a decomposition.
No, it's a double displacement with a decomposition. Or a double replacement reaction with the decomposition.
Okay.
So you're saying 2 here and 2 here. Okay, now does everything add up? Okay. Yeah, it's like, nope, look at that. Yeah. Yeah. It's like, I'm not gonna behave today. My plus, my cross, it won't move over. It's like, nope, there we go. Yeah. Okay. Okay, so then the total ionic equation. Okay, so it's 2 Na plus AQ plus, okay, the carbonate ion. What is the charge on that? 2 negative, that's right. AQ plus 2H plus AQ. And I heard plus Cl minus AQ. And there should be two of those, right? And that's going to yield to Na plus 2Cl minus AQ plus carbon dioxide plus H2O.
So would the spectators be the sodium and the chlorine?
The spectators would be the sodium ion and the chloride ion.
Oh,
Yep.
sodium and chloride ions. Okay.
Yep. So okay. So what's left over? The carbonate ion and the hydrogen, two hydrogen ions. And that's going to yield and water. That's right. Okay. Questions? Nope. Okay. Can I erase? Are we ready?
I'm
Or
not
do
sure
you-
if this is is this a useful reaction in terms of does this can we do anything with this, or is this
Well,
more
actually,
of
this
a-
is something that kind of happens in nature, but not necessarily with hydrochloric acid. So,
Okay.
like in the case of carbon dioxide, carbon
Mhm.
dioxide gets into the atmosphere. Too much carbon dioxide starts interacting with some of the water. It starts to form carbonic acid, but that carbonic acid breaks down to back down to carbon dioxide and water. Okay.
Okay.
It forms this nice little cycle that happens. Okay. But during that time period, it becomes acidic because it's acid rain. So it'll start raining acid rain. So it basically has that H plus added on into the water. And then as a result of high elevation levels of carbon, right? Because this reaction here, this unstable reaction, it actually forms what we call an equilibrium. And so if we increase the amounts of this and there's water present, it causes this to form. Well, then that acid starts falling to the ground. Although it's unstable, it'll start killing things on the ground eventually. And then it breaks down to carbon dioxide and water.
Okay.
So it does its damage and then it leaves. Sort of.
Is there any engineering application?
There probably are. I mean, because we use carbon dioxide for so much stuff, right? Actually, we don't. That's my point. We have so much of it in the atmosphere that's not good. But if somebody could just figure out something to do with it, that would be great, you know.
Okay.
Although plants use it, but we kind of, yeah, but not enough. Yeah, exactly. Yeah,
Plant more trees.
plant more trees, exactly. Yeah. Okay.
Thank you.
No problem. Can I clear? Okay. Next. Okay, so next thing is, so sometimes we could have reactions with undissolved reactants. So in the case that we have something that's undissolved, we still describe it as the state that it was initially at. So if it was a solid, it's a solid. If it's a liquid, it's a liquid. If it's a gas, it's a gas. Okay, even though it may dissolve in our solution, we're still going to describe it initially as being acid. Okay. And then even though that we have a solid that may remain a solid initially in the reaction, it can still react. Okay, so let me give you an example. So we have solid aluminum hydroxide dissolved in hydrochloric acid. So when we write the chemical equation for this, it's going to be aluminum hydroxide,
AlOH3.
AlOH in parentheses and a 3. Okay, solid, liquid, or gas.
Okay, solid.
Okay, dissolved in hydrochloric acid. Solid, liquid, gas, or aqueous. And our product is going to be
Aluminum chloride and water.
So aluminum chloride is AlCl3.
Cl3.
Is that going to be a solid, liquid, or gas?
It's going to be aqueous.
Or aqueous.
I think
You guys have your table. It's soluble. And our other product is going to be solid, liquid, gas, or aqueous. Okay. So our our total ionic equation, Al, are you sure? That's a solid. So we keep it together. Is that what you're telling me? Okay. Plus aqueous, H plus aqueous, plus Cl minus aqueous. And that's going to yield three plus aqueous plus H2O. Who are our spectators?
the aluminum and the chloride or chlorine.
Are you sure?
Uh,
was this balanced anyway? We didn't balance this. Oh, so let's do that. How many waters do we get? Let's see.
Would this also be called aluminum chloride hydrate?
Aluminum chloride hydrate. No, aluminum chloride hydrate is different.
Okay. How so?
Because aluminum chloride hydrate means that you added one hydrogen or one water molecule added onto it. So it would be AlC3.H2O. That's different.
Oh, I see. Right. Okay. So then this is.
Yeah. So don't mix them up. This is still a reaction. This is
Okay.
aluminum hydroxide reacting with hydrochloric acid. That's not the same thing.
Okay.
Okay. And they have to be, for it to be a hydrate, it has to be captured by, it's really captured by the metal, in all honesty. So, okay. Now, so what were the spectators? Sorry, I missed that. Okay, so the chlorides are spectators.
Did we determine if it was already balanced or not, or did we?
We just
we
balanced
just
it.
balanced it. Okay.
Yeah, we just balanced it. Okay, so the net ionic equation. Is that correct so far? And 3 hydrogen ions, AQ, yields aluminum ion and 3 waters. Okay, questions? You guys are good? Okay. So there's one more major slide that we have to go over, then we'll do a summary. Okay, you guys are ready? Let's see, what time is it? We're not doing too bad here. Okay, clear. Okay. Okay, so I'm going to use your guys' knowledge. You guys are geniuses now. So we have sodium chloride, a solution of sodium chloride. Is that going to completely separate, or is that going to stay together? It's going to completely separate. And we have a solution of potassium nitrate. Is that going to completely separate or stay together? It's going to completely separate. Now, if we get potassium chloride, is that going to form a solid? Or is that going to form an aqueous solution? Okay. And if I said potassium chloride, and he says aqueous because it's nitrate. What was that? But it is aqueous. You're right. It is aqueous. Yes, but why is it aqueous? Why is it aqueous? Well, so potassium nitrate is going to be soluble, but
It's a group.
Potassium chloride. Why is potassium chloride soluble? Because it's a group 1 metal.
Yeah.
That's right. So we know that group 1 metals, and it's also with chloride, which is often very soluble, right? Okay. So that's going to be aqueous, and the sodium nitrate we know is aqueous because you told me nitrate is always aqueous. That's right. That's right. Yeah. Okay. Now, if we look on both sides, we have aqueous, 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 aqueous. There's no liquid. There's no gases. There's nothing, right? So that tells me that everything separates, right? So if everything separates on both sides, that means we have only spectators, right? So if you have only spectators, let me write that down. Let me show you, because we get Na plus Cl minus. Those are AQ, both of those. AQ plus K plus AQ plus NO3 minus AQ And we get exactly the same thing on the other side, right? K plus AQ plus Cl minus AQ plus Na plus AQ plus NO3 minus AQ. I can't see my AQ. I ran out of room. Okay. So in this case, both sides are full of spectators. Nobody's doing anything. So this reaction won't happen. Nothing's going to happen. You're just putting things in solution. Nothing's happening. Okay. So you would get NR, no reaction. Right? You guys get that? You see it? Don't cry. It's okay.
Well, I understand that they're all spectators, but
But are you getting a product? Are you making anything?
well, you're just switching out the.
But you're not, because they're not reacting. They're not physically binding to each other, right? Because they're
Oh,
aqueous.
because they're Okay, I
That's
see.
right. So you got to remember, even though we write it as if they're physically binding with each other, because they're aqueous, they're just ions in solution,
Okay.
right?
So it just,
So they're free. They're free willy, you know?
yeah. So
There's nothing that's pulling them together.
so basically, you just got a solution of nothing.
That's right. Right. So everybody's spectators. That is a boring ass party. Right.
That sure
Right.
is.
Nobody got any action that night. So, okay. Okay, so that's clear. Do you guys understand that? So you want to remember that's no reaction. Okay. Now, I'll give you guys a hint. I had one exam that I had this really long problem. It was hard too. I mean, it was really hard. But the first thing that you have to do is recognize that there was no reaction, right? If there's no reaction, you can't do anything with it. I'm just saying. Okay. Okay, so this is just a summary of everything that we talked about today. So this is a good place to go to for making sure you got a clear understanding today and I guess last week. Okay, questions, concerns?
Oh, yeah. So for we were using hydrochloric acid a lot.
Yes,
If we used a weak acid, like
yes. So if you use a weak acid, you're going to get a reaction, but you have to remember a weak acid isn't going to completely dissociate. So it's going to react, but it may be a slower reaction as a result of it.
okay.
Okay.
And
But
would that
that is actually a good question. And in our context, we probably won't do it too much unless it's with water, because then you're always gonna get something happen.
okay.
Okay.
And the only weak acid that comes to mind is like carboxylic acid. Is that COOH or is that something different? Or is carboxylic a class of
Well, you
carbon?
could get oxalic acid. That's that is a weak acid. Citric acid, another weak acid. As you were saying, salicylic acid, another weak acid. So any carbon acid, yes, that would fall into that context.
Okay.
Yeah, but you're not going to see anything like that on the exam because we're primarily focusing on inorganic molecules, not organic. So,
Okay.
okay. You may get something like acetic acid, but that's the extent of it.
Oh wait. Now for the rabbit hole. And not everything that has carbon makes it an organic compound, right?
That's true. Not everything that has carbon makes it organic compound. So typically, if it's carbon dioxide, it's not considered to be organic. That's considered to be inorganic because it only has that one carbon. And then if you have not carboxylic acid, if you have carbonate, that's not considered to be organic.
because it's just the one carbon.
It's just the one.
But if it's
Acetic acid is kind of like that borderline. It
Okay.
is considered to be organic, but there are some people that try to say it isn't, but it is. Acetate, organic.
okay,
Citric acid, organic.
so basically 2 or more carbons makes it organic.
Typically, except for
Okay.
methane. Methane is considered to be organic.
Okay. I'll put that for the
Okay.
memory banks. Thank you.
Any other questions? No, no, no?